and out, so forgive me that, but I can't sit still. And I forgot to turn off. I'm kind of wacko, if you haven't noticed. Okay, but what I didn't do was get out of, this is what threw me off, out of PowerPoint for my last class. So in that, and in this, and go to this. I could have done this a much faster way, but I didn't. Okay, here we go. Math 113. All right, we'll start at 4.1. And my Math 112, we start at 1.4. This one we start at 4.1. So that's loading. But before we get there, I want to make sure all of you are on board and on the same page with what we're doing. Any questions? I've said it before, but I'll say it again. Any questions on the preliminary stuff that hopefully you looked at, or you're not sure about, or I ran on and on and on and you fell asleep when I was talking? Anything. Do you have any questions on how we're going to do the course? Okay. Now, same text that you used for Math 112, you did chapters 1, 2, 3, and maybe 7, or into 3, maybe 7 if you got that far. The reason you skipped 4, 5, and 6 are the trig chapters. So that's what we're doing in this course. Okay. Y'all all know and understand Blackboard, have no questions about it, right? Okay. So let's get started then, I guess. How about office hours? Do you understand them? Did you look at them? Probably didn't have the most current one. Let me do say this. If you last week looked at Blackboard, except for the YouTube videos, the cupboard was bare. Okay, there was nothing else there. But since my wife had surgery on last Thursday, I was in the waiting room for long periods of time. I got just about everything updated. All the syllabi, my locator card, the research paper instructions, everything that I could do, I got done while I was there in the waiting room. Then I took her home. She was doing really, really well. I actually had a little bit of wondering if I should come on back into campus that afternoon, but she fell asleep, and I didn't want her waking up, especially if she had complications and nobody in the house, so I stayed there. So that's when I got everything loaded on Blackboard. So now on Blackboard, and let me go over this a little bit. When you go to the home page for this class, there's a series of tabs here. Now, between last term and this term, they've changed it around, so they do it pretty frequently. There's a group of tabs here, a group of tabs here, and then some more groups further down. In the first group of tabs, somewhere about the third one, it says syllabus and book information. If you click on that tab, then you see the syllabus for the course. You have to click on that. You don't see it. You have to click on the place, the name of the syllabus, and you'll get it. Then if you go to the next tab over here, the blue tab over here, it says instructor information and office hours. Okay, if you click on that one, then what shows up here is my locator, well, the name locator card. You click on that and you see it. Let me just, I know if you look at it, you can see it, but I've wound up, much to my chagrin and even worse to my wife's chagrin, right now teaching 10 courses this term. I'm supposed to do no more than 4, okay? But people need it to graduate, and we're just short. Yeah, so some of them I'm not getting paid for, that kind of stuff. But I'm glad we got more than 10 students in here to get paid for this class. Good, thank you. All right, but that means I don't have many office hours. So let me go over those right now. On Monday and Wednesday mornings from 8 to 10, I have office hours, okay? The reason is I gave away one of my courses, okay, that was an 8:30 to 9:45 course. So I'm usually here before 8 most mornings, and my first class on Monday and Wednesday starts at 10. So 8 to 10, my office is 265. And does everybody know where that is or have a general idea? If not, I can show it to you pretty quickly. Anyone need to know where that is? All right. Then, Monday afternoon, I have at 10 o'clock a Calculus 1. At sometime 12:30, I have Calculus 3. And at something like 2:30, I have differential equations. From 3:45 until 6, that's my next big chunk of office hours. Okay, 3:45 till 6 on Monday. Not on Wednesday. I'll get there in a minute. On Tuesday and Thursday, unfortunately, I have almost no office hours. 8 to 8:30, Tuesday and Thursday. Okay? But then I have pre-calculus algebra at 8, at 8:30, this class at 10, linear algebra at 12:30, and then I have from 11:30, and from 12:45 until 1:15, a half hour there, that's my lunch. Okay? I eat in my office, so you're welcome to come by then. Okay? 12:45 until 1:15. Then at 1:15 in the afternoon, both first and second mini terms, I have physical science classes. Physical science 1, first mini term, physical science 2, second mini term. They go from 1:15 in the afternoon, the class goes till 3:45, and then the lab goes 3:45 to 5:45. So basically, I'm out of pocket from 1:15 till 5:45. So I'm back in the office from 5:45 till 6. Now, not today. I've got to sit on the help desk today from 5:45 to 6. What a joy. But it won't be too long. Usually I'm here after 6, so if you need to see me after 1:45, I'm either up here ending that lab or down in my office. So catch me there. Wednesday, the 8 to 10 is still good, but the afternoon is not because I have a physics class over on the Birmingham East Campus from 4:30 to 6:30, so I have to leave here shortly after 3:45 to get there. Yes?
How many physics classes do you have? How many physics classes do you have?
Just that one.
Is that one?
Yeah. That's one for the sonography program. It's the physics they need for that. It's just a 2-hour class, so I teach it one day, 2 hours, 4:30, 6:30 on Wednesdays. That's why it didn't take up Monday also. Now, Fridays, that's my biggest chunk of office hours, but I'm over on the Birmingham West Campus most Fridays, and that's 8 to 12. So I'm usually there before 8 and just about always there after 12. Okay. Now, I do know of 2 Fridays I will not be on campus, or at least I know of one. The other one I think I won't be. The first is the first Friday in February. We have math meetings in Tuscaloosa, so I'll be there that Friday. I have a mild form of leukemia, and usually about once a term I need treatment. So I'm guessing that will be some Friday, February, March, April, sometime like that. Possibly May, I don't know. Depends on what my counts are. The counts have been very, very good, so I'm hoping to delay a treatment as long as possible. So I might even get out of the term without one. But typically I have one Friday, at least one Friday I have to be gone. Okay, now they also love calling meetings on Friday, so check with me before you come. If I know of the meeting coming up, I'll let you know what times those are. For instance, we got one the last Friday of this month, but it's a 12:30 meeting, so it's after I'm supposed to have gone home, but I'll be hanging around for a meeting. Okay. Thought I needed to say that just because I have so few office hours. Monday, Wednesday morning, Monday afternoon, Friday morning. Little bit of time on Tuesday and Thursday, and that's all. Half hour, 45 minutes. 15 minutes, sorry. All right, any questions? All right. Then, if there are no questions, let's get started on the real stuff. Sure. Anyone know what trigonometry means?
Study of triangles.
Second?
Study of triangles.
A little louder. I'm hard to hear.
Is it the study of triangles?
Yes, absolutely. The study of triangles. The trig, that's the triangle part. The metra is the measure. Okay, so it's the study of the measure of triangles. Now, we're going to do more than triangles, and it certainly has grown to more than that. In fact, we don't even start out talking about triangles, okay? 4.1 is talking about ways to measure angles. And most of you are probably familiar with degrees, not temperature degrees, but angular degrees. Okay? I'm hoping some of you are at least vaguely aware of what a radian is. If not, we will go over that in gory detail. Okay? So our objectives in this section are to describe angles, before we ever get to a triangle, describe angles. We'll use radian measurement, we'll use degree measure, and we'll talk about how you can go back and forth between the two, and we'll use angles to model and solve some real-life problems. Now, you'll see this type of a statement as the last objective in just about every section. Whatever we've done, use it to solve some real-life type problems. Okay, so let's start with angles. Okay, where do we begin? As derived from the Greek, and here's, I think he was looking ahead, the trigonometry means measurement of triangles. Okay? So initially, trigonometry dealt with the relationship among the sides and the angles of triangles. That's where it came from. And we're not going to even talk about a triangle, except in these kinds of contexts, for a while anyway. Okay? We're going to start with the unit circle, which is not a triangle. Okay? So an angle, okay, which is certainly in a triangle, is determined by rotating a ray. Now, what we mean by a ray, not something that stings you, but this is something, okay, a line goes infinitely in both directions. A line segment is terminated in both directions. A ray is in between the two. Terminal on one side goes infinitely in the other side. So that's a ray, and if you rotate a ray, or a half line, about the endpoint, you form an angle. That little thing here would be the angle. Between the initial side and the terminal side, that would be the angle. It's not a length, it's not anything except how much it's rotated. So the starting point of a ray is the initial side. Say if it was starting here, I did mine horizontally, you can start it anywhere. And the terminal side is where it ends up. The angle is the amount of motion around that endpoint, which we now call the vertex. Okay? So this is what we call the angle between the initial side, terminal side, about the vertex, or the endpoint of those rays. Okay? Now, if I ask you how to measure those, most of you probably say degrees, and that's what we're used to doing. Okay? There are other ways, at least one other way to measure that we will really focus on and actually wind up using more than degrees. Okay? So the endpoint, as I said, is called the vertex of the angle. And the precession of an angle, if you put it on a Cartesian coordinate system and put the origin at the put the vertex at the origin, where the origin is the vertex, and the initial side is the positive x-axis, in other words, the horizontal side there. If you do that, this then is sort of our standard way of referring to it. And then move from there to wherever the terminal side is, here. Okay. Now, especially if you have it on a coordinate system, what can you tell me about that angle? Just looking at it. Okay, more than 90 degrees. Okay, always put the unit with the number that you're talking about. More than 90 degrees, because the y-axis would be 90 degrees. So this is greater than a right angle, and we'll have names for that we'll get to later. I won't get to that yet. So such an angle is said to be in standard position when its initial side is along the positive x-axis, and terminal side is somewhere. Okay, and here's the other thing. Generally, we rotate counterclockwise. Now, I don't know that there's any really good reason we do counterclockwise. It's just this is the tradition, okay? We always call this the first quadrant. You can see the two axes divide up the whole plane into 4 equal pieces, okay? So they're each a quarter or a quadrant. Anyone know why we call this the first quadrant? Everything's positive there. We like positive, don't we? So that's the first quadrant. And then just tradition has that we call this the second, third, and fourth quadrant. We're going to get into that later, but that's sort of standard. You can rotate the other way, but then you usually talk about a negative angle. So positive angles are angles rotated counterclockwise, negative angles are those rotated clockwise. I'm jumping ahead. I should have waited till they caught up. Okay. And here it is. Counterclockwise rotation generates positive angles. Clockwise rotation. Now, I guess what happened, whoever made clocks made them go the wrong direction. If we had just started making clocks go that way, then everything would be clockwise and it would make sense. Okay, but it doesn't. Okay, so counterclockwise rotation generates positive angles. Clockwise rotation generates negative angles. It's shown here. Okay, both of these standard angles, the standard position, because your initial side is the positive x-axis. It doesn't have to be, but that's how we usually like to write it. Now, angles are often labeled with Greek letters, whereas distances are usually X, Y, Z, those kinds of things. But angles quite often listed with Greek letters. Alpha, which corresponds to our little a, beta corresponds to our little b, theta corresponds to, I don't know what, it's not T, that would be tau. It doesn't have anything it corresponds directly to, but the reason I mentioned it, or they mentioned it, is everybody's favorite angle is theta. You know, just like X is everybody's favorite variable, okay? Well, theta is usually the angle of choice. It's theta. Time of theta, you know, whatever. As well as uppercase letters, capital A, capital B, and capital C, okay, or any other capital letter. The reason capital letters are often used is when you did have a triangle, you usually label the vertices A, B, and C. So that's why they mention those here. Capital letter A, B, and C. The length we do lowercase letter A, B, and C. Okay. Now, note that any given angle, in these cases alpha and beta here, have the same initial and the same terminal sides. Okay? Strange but true. So initial side, positive x-axis. If you rotate counterclockwise around to here, there is your angle alpha. Now, here's something they've done. They started off talking about these as being rays. Now they don't draw them as rays anymore. They look like line segments. So it really doesn't matter whether you call it a ray or a line segment. Okay? If it's in a triangle, they're going to be line segments. But they started off naming rays, but they gave it up really soon. So there's that. But if you did the clockwise rotation and made this the negative angle beta, that's the same angle. Same terminal side, initial side, same terminal side. So these two are co-terminal angles, meaning they share the same terminal side. Co means with, you know, so they're with the same terminal side. Now, if you did them both counterclockwise, both positive angles, here's alpha, but beta, you're going to pass it once and come back around. There's beta, same terminal side. Okay. Now, can anyone look at this and tell me a relationship between alpha and beta? This one, the first one. Anything? What happens if you add the positive value of alpha here plus the positive value of the negative angle, in other words, the absolute value of beta here, what do you get?
360.
360 degrees. Later we'll name that in radians too. So the sum of the absolute values of these is 360. How about these two? How are they related? Second cousin, twice removed. How are they related? Beta, you start here and go alpha, and then you go how much further? How much further? One complete circle. So the difference between these two is 360. The sum of the absolute values of these is 360. The difference of those two is 360. Okay? Now, this isn't quite as clear, but I will say it. This is alpha. If I were to subtract beta, which is a negative angle from it, that's subtracting a negative, the same as adding. So actually the difference between these two is also a 360. It's not as obvious, but it is. Okay. So basically any two coterminal angles, the difference between them is some multiple of 360 degrees. Because you could have taken gamma here and go around and around and around so many times and stopped here. However many times you went around, that's a multiple of 360. So the difference between two coterminal angles is always a multiple of 360 degrees. Okay. That's beyond what they're doing here, but no extra charge, okay? Not going to charge you any more for that. Now, let's talk about what we mean by radian measure. We've been talking in terms of degrees so far. Let's talk in terms of radians. Okay, I need to keep turning my pages of the book to make sure that I don't leave something out. Sometimes the slideshow will leave things out that are in the book. Okay. Determine the measure of an angle by the amount of rotation from the initial side to the terminal side. That's what we talked about before. One way to measure that, we talked about degrees, which are sort of a made-up construct. The other is a radian. Now, here's a problem with radians. It's not really a unit. Okay, degrees is some unit someone made up. Okay, a radian really isn't. What a radian is a ratio. Okay, now, what's a ratio of? Well, one part of radian comes from the word radius. So it's a ratio, and part of that ratio is the radius of whatever. And here we are on a unit circle, or on some type of circle. It doesn't have to be a unit circle. Okay? So here's what we're doing. Measuring radius. This type is useful in calculus. And the reason for that, when we get there, this is pre-calculus. That's where we're heading, right? Oh, I shouldn't bang on the desk. I have a sensitive connection back there. Okay. In calculus, when you take a derivative or integrate anything to do with angles, you want to be in radians because they work out nicely. If you're in degrees, you have strange factors you have to incorporate to make it work. So that's why we say especially useful in calculus. So here's what a radian is. Let's give a definition here. Let's say we're on a circle of radius r, okay? And that's going to be our initial side is going to be the horizontal side of that, positive horizontal side, and that's going to, of course, be a length r, because you're center of a circle here. Okay, and let's say we move this far, okay? Now, same radius, because that's you're in the center of the circle, okay? So the radius is the same. The amount that you traveled here is called the arc length. The arc length of that circle for this angle theta. For that angle theta, this is the arc length of that circle of radius r. Okay? Now, when that arc length is exactly equal to one radius, okay, so you took this line, you put it here, and you bend it around and stop right there. When that s is equal to r, this arc length is equal to the radius, this angle here is 1 radian. The ratio of the arc length to the radius is 1. Anything less than that, that radian would be less than 1. The measure of that angle would be less than 1. Anything greater than that would be greater than 1. Okay? So that's a radian. It's a ratio. Okay? Arc length measured in whatever you want to measure it. Centimeters, millimeters, inches, furlongs, whatever. Okay? And measure the radian in the same unit. It's a ratio. It has no units. It's not a unit. Now we use it, we write it as if it's one. We say 7 radians or 4.3 radians or pi radians. As if it was a unit. It really isn't. That means how many ratios? Okay, how many times the ratio of the length of that angle right there. So that's called the central angle, and it's measured in radians as its ratio of the arc length that cuts to the radius. Okay, so that's an arc length of equal radius when theta is equal to 1. So here's the definition of a radian. 1 radian is a measure of the central angle theta that intercepts an arc length s equal to the length of the radius of that circle. Okay? Where the central angle of the circle is where the center of the circle is at the vertex of that angle. Now, when you do that algebraically, that means theta is the ratio of the arc length to the radius. Theta is equal to s over r. Where theta is measured in radians. Okay? We treat it as if it's a unit, but it really isn't. It's 1. It just happens we would call it radians. Note that theta is equal to 1 and s is equal to r. Okay. Now, whenever you have a relationship like this in a multiplication or division sense, you can come up with 2 more automatically. Anyone think of what they would be? Let me get my pen set up. Anyone think of another expression? It says the same thing as that, but rearranged. Let me do it algebraically for you. Multiply both sides by r. Multiply this by r and that by r. Here the r's cancel out, right? And what do you have? S is equal to r theta. Okay? Now, we solve for theta here. We solve for s here. What's left to solve for? R. Okay? So you could divide both sides of this by theta, and then that would give you, here the thetas go out, r is equal to s over theta. Now, that's not really all that important right here, but it does give you a few tools that you can use when necessary. Very seldom do I really use that one. This one, though, I use a lot. S equal r theta. Okay? And I think you will too. Now, I was in the U.S. Navy. Now, mathematics and doing things and multiplying and dividing, I understood that and I followed it. But when I was in the Navy and had to go to Navy schools, evidently a lot of people that had to go to those schools weren't that familiar with variables and manipulating and stuff like that. So they came up with these little things, and I've seen it elsewhere too, so it's not just the Navy. Came up with these kind of things. Either a circle or a triangle. I kind of like the triangles better, but circles are fine too. And you draw 2 lines, a horizontal one and a vertical one. The horizontal line is the division line, you know, something divided by something, that's the horizontal line. The vertical, we make it a multiplication line. Now, if you take the thing that's on top, or the thing that the other 2 multiplied together, and put that on top. So S here, and then put your R and your theta down here, R and theta here. It works the same way. It's the same principle, just whether you like circles or triangles. If you're looking for any one of these, S is equal to R times theta, R is equal to S divided by theta, and theta is equal to S divided by R. Okay, so you can get them. So if you don't like remembering or memorizing, or you want a little mnemonic device, this is really helpful. It works with many things, Ohm's law, power form. I mean, there's just all sorts of equations that work by multiplication or division, 3 variables. You can always set them up to do this. Okay. You don't have to, but it's just a fairly easy thing to do. All right. Now, let's think about what happens if you go 1 complete circle. Okay? Here's your initial side, and you're going all the way around. What arc length have you just cut? What is that called? If you had a circle of radius r, what do you call the distance around that circle? Circumference. Does anyone remember the formula for our circumference? 2 pi r. 2 pi r. There it is. arc length, when it's a complete circle, circumference is equal to 2 pi r. Whatever your r is, 2 pi times that is your arc length, right? Now, what would be the radian measure of that? The radian measure is s divided by r. And if you divide this side by r, this by r, that gives you theta. And what theta do you get? 2 pi. All the way around the circle, no matter how big or small the circle is, the angle is, that was supposed to be a theta. It came out of phi. I don't know how that happened, okay? Let's see if we can get that corrected. Okay. Duh. What did that say? Where did that come from? Okay, theta is equal to 2 pi. All the way around the circle, the radian is 2 pi. What do we call that in degrees? 360 degrees is the same as 2 pi radians. Okay, we'll make it a little simpler later. Divide both sides by 2, and what do you get? If this 2 pi is 360 degrees, pi would be 180 degrees. That we're going to use over and over again. Not yet, but we're going to use it. So hang on to that thought. Okay? So, y'all know what pi is? R? No, never mind. Pi? 3.14, approximately. So therefore, 2 pi would be 6.28, approximately. Okay? It's an irrational number. It goes on and on and on. Okay? So that means that one time around the circle is a little bit more than 6 radians. 1 radian, 2 radians, 3 radians, 4 radians, 5 radians, 6 radians, and then another close to a quarter of a radian to get that last little bit there. Okay? Just to give you an idea. Okay. Now, if this were exactly 6 times around, that would be, if you divided the circle into 6 equal pieces, a little bit more than 6 radians, but a little bit more than that, that would be 360 divided by 6 is 60. So 60 degrees would be just a hair further than this. And then 60, 120, 180, 210, 270, yeah. Anyway, you get all the way around and you're back to 360. Okay. But anyway, so a radian is a little less than 60 degrees, is what I'm getting at. Okay? It's around 57 point blah, 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 another irrational number. But it's just a little less than 60 degrees. Okay? Just to get the concept in there. Because the units for a measure of S and R are the same, inches, centimeters, furlongs, whatever, the ratio has no units. It's just a real number. Okay, a ratio, no units. We say 5 radians, but that should just be 5. Okay, but then you say, well, 5 what? You know, 5 of the ratios of the arc length to the radius. Okay. Now, so here's getting toward what I was saying earlier. If 1 complete revolution is 2 pi radians, half a revolution would be half of 2 pi is pi. A quarter of a revolution, that would be from here to here, that would be half of this, which would be pi half radians. Get used to that. You're going to stop saying 90 degrees and start thinking pi half radians. If you only went 1/6 of the way around, then you're take this and divide by, I'll take this and divide by 6, and you get pi third radians. And that's your 60 degrees. Okay? Pi 6 radians would be 30 degrees. Pi quarters radians, oh, we already said that. Pi quarters radians would be 45 degrees, exactly half of 90. Okay? So get used to these. Those are going to be our favorite angles, okay? And whether you measure in radians or degrees, okay? Here's a picture of that. I like to start here all the way around and notice 2 pi radians. Halfway around would then be half of that pi radians. Half of that would be pi halves radians. That little symbol there means 90 degrees, perpendicular, orthogonal, right angles. Yeah, that's what that thing there means. That's 90 degrees or pi halves radians. Okay? This time we're not going in quarters. Let's go in sixths. Okay? 1/6 of the way around here would be 2 pi over 6, which would be pi thirds. That would be that. There's 1, 2, 3, making up pi. So 3, a third of a pi, pi thirds. If you took this one and split it in 2, I would have done this here. That is pi fourths. Half of pi halves is pi fourths. And that's our good old 45, right? And you got 4 of those equals in there. Okay? And if you did 6 of these, rather than 6 of the whole circle, or 12 of the whole circle, that would be pi 6. And 1/12 of 360 is 30 degrees. Okay. So there are going to be your favorite angles in radians. Pi, well, 2 pi, of course, pi halves, pi quarters, pi thirds, pi 6. We're going to do a lot of things with those angles. Okay? Then we'll do them with other angles and things that are a little more complicated. These are really nice, rememberable angles. Okay? And of course, pi 6 is exactly half of pi thirds. 30 degrees is half of 60 degrees, if you want to think in those terms. Any questions on that before we move on? All right. Now, as I said before, tradition has it, we number the quadrants 1, 2, 3, and 4 counterclockwise, so that's why we have to go this way. Okay? Usually they use Roman numerals 1, 2, 3, and 4. You don't have to, but it's usually that's sort of the standard. And if you think of the angles as you go positively, that would be 0 to pi halves to pi, pi to 3 halves pi, and 3 halves pi to 2 pi, which you're back to that equals 0. Again, exactly a multiple of 360 or 2 pi. 360 degrees, 2 pi radians. Okay. Now, if you're in the first quadrant, okay, you already told me something about that. What's true about the first quadrant? Yes, the x and the y are both positive there. Okay? The angles you get when you're in the first quadrant between 0 and pi halves, not 0 nor pi halves, but anything in between those two, we have a special name for those. They're acute angles. Oh, acute angles, okay. Those are acute angles, okay? Now, if you're in the second quadrant, we don't have names for the ones down here, but second quadrant, you're beyond 90 degrees, or pi halves, but less than pi, they're your obtuse angles, okay? And those are called obtuse angles. So an angle between 0 and pi halves, or 0 and 90 degrees, is an acute angle, and anything beyond that up to 180 degrees, or pi radians, you're an obtuse angle. Okay, just a couple of names just to give you something else to think about. Okay, but we'll use these terms very frequently. Okay. Now, if I ever get to going too fast and get off the slide before you finish with it, stop me. I'm not offended, you know. I'll stop. Okay. Now, we've already talked about this before figuratively. Now let's talk about it in terms of radians. Two angles, coterminal, when they have the same initial side and the same terminal side. For example, 0 and 2 pi, remember I said that, there's 0. If you're all the way around to 2 pi, you're at the same place, okay? So those are coterminal angles. As are pi 6, and add 2 pi to that, you get 13/6. This is 1/6 pi, that would be 13/6 pi. What's the difference between those two? 12, 6, 5. 12, 6 is 2, right? Difference between these, 2 pi. Difference between these, 2 pi. Okay? So you can find an angle that is coterminal to any given angle, theta, by either adding or subtracting 2 pi to it. One revolution. Before we were saying 360 degrees, 2 pi radians. Okay? We're going to do that in example 1 that's coming up. Now, because all coterminal angles are really the same angle, anytime you're talking about some angle theta, it has infinitely many coterminal angles. All you do is add 2n times pi. N is any integer, 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, 0, you have any integer, 2 times 2 pi times that n. That's how many times around the circle you go. That's your n. Times 2 pi. That will give you a coterminal angle. So if you started with pi 6, and then go 1 time around, that's 13/6 pi. Go 1 time around negative, that's negative 11/6 pi. Okay? Go 7 times around, it's 7 times, that would be 14. Pi 6 was 14 pi. That would be, you have to multiply 14 times 6. It gets big, hairy numbers, but it's all doable. Okay. Does that make sense? So basically what we're saying is the difference between an angle and a coterminal angle, the difference between is some multiple of 2 pi. Always. Okay. Which we noted at the very beginning. Okay? So, the first example we get are going to be finding some coterminal angles. So, stand by for that. That's going to be in example 1. So, give me some other angle. One of the favorite angles I said we'd be running into. Name one of them. They mentioned pi 6 here. What was another one? Pi what? Pi thirds, okay, pi thirds. What would be a coterminal angle for pi thirds? Second? Coterminal angle for pi thirds. Add 2 pi to it. Well, if you're dealing with thirds, that would be adding 6 pi thirds, right? 6 pi thirds plus a pi would be, 1/3 pi would be 7 pi thirds. There would be a coterminal angle. So let's see. All right. For the positive angle, 13/6 pi, subtract 2. I hate it when they do the exercise this way. Why didn't they just say, find a coterminal angle to that? How would you do it? Got one or two choices. You got many choices. But what I would do would be either add 2 pi to it or subtract 2 pi from it. Okay? Well, 2 pi and 6 is how many pi? How many 6 of a pi is 2 pi? 12/6 pi. So either subtract 12/6 pi from that, what you'd get? Pi 6. Or add 12/6 pi and you get 25/6 pi. I don't know if that's too big a number, but yeah, it's fine. You can either, here's my, the first angle we had was 13/6 pi. Now remember, 1/6 pi, 2/6 pi, 3/6 pi, 4/6 pi, 5/6 pi, 6/6 pi, 7/6 pi, 8/6 pi, 9/6 pi, 10/6 pi, 11/6 pi, 12/6 pi, 13/6 pi. There you are, okay? Subtract 2 pi from it, so back up exactly 2 pi, and you're back here at pi 6. Or add another 2 pi to it, and you're at 25/6 pi. That's what you do. Add some multiple, add or subtract some multiple of 2 pi from your given angle, and you have the coterminal angle. That's the easy one, because just subtract it. Rather than subtracting 2 pi, I would subtract 12/6 pi, because that is 2 pi. Just makes the subtraction easier. Okay? Does that make sense? Okay. Now, I wish they had just said to do it and not telling you how to do it and then say, okay, you've done the example. They did all the thinking for you. Wish they'd let you thought yourself. Okay. Okay. Let's do the B part. Now we have a negative angle. Negative 2/3 pi. Where in the world would that be, Waldo? You start here, and if you're going negative, there's negative 1/3 pi, negative 2/3 pi. There you are, right there. So find a coterminal angle to that. What would you do? What would you do? Either add or subtract 2 pi from it, or some multiple of 2 pi. It'd be easy to add 2 pi. Now, in terms of thirds, how many thirds is 2 pi? Is 2 pi? 6 pi thirds, okay? So add 6 pi thirds to negative 2/3 pi, 2 pi thirds, and you get positive 4/3 pi. Well, there's 1/3, 1/3, 2/3, 3/3, 4/3. Yep, there you are, right there. So there you are at 4/3 pi. Or you could have subtracted another 6/3 pi from it, be it negative 8/3 pi. That would have been going here and then going one more circle around. And that would have been. All those are coterminal angles. You have an infinite number of them. I like going with the easy ones. Okay? Does that make sense? Yay or nay? Okay. Yay! All right, good. All right. All right. Oh, I thought there was a C part. There's not. And by the way, for those who are not familiar with the book, let me point something out to you. Every one of these examples you'll see in the book, I'm pretty sure, it seems like it is, after you do the example, there's immediately following that a checkpoint, which is a similar example, but you do on your own, okay? And if you can't get those, look here. Audio, video solutions to these checkpoints in both English and Spanish are available at larsonprecalculus.com. Okay? So there is a free website. You don't need a code. You don't need anything. Anyone can go to it. larsonprecalculus.com, and you can go and get the answers to the checkpoints. Okay? Good thing to do soon after class, because I'm up here doing most of the yakking here. I'm asking y'all questions. You're giving me good answers. Yes, of course. But as soon as you can after class, do the checkpoints of all the ones we did in class, so you get it into, and it becomes yours, not mine. Okay. So do those. If you need more help with it, by all means, go to larsonprecalculus.com. Okay. Now, okay, that was 1B. Now we move to a couple of definitions. Now, a couple of things here. These are both positive angles, alpha and beta. Always positive when we're talking in these terms. Two angles prove positive angles, alpha and beta, are complementary. Now, that doesn't mean, oh, your hair is nice today. Not that type of compliment. This is an E in there, not an I. Okay? Now, what word do you almost see with complementary? Complete. Exactly. They complete what? Well, the Greeks had this notion, and you sort of see it in its name here, that the perfect angle, let's guess which angle. Say again? Yes, the right angle. That's why they call it right. It's perfect. It's right. Okay? So, two angles are complementary, complete each other. When you add them together, they complete a right angle. Pi halves. So, two angles are complementary. They're complements of each other when their sum is 90 degrees, or pi halves. Not the right angles. Now, they're supplementary. One supplements the other when their sums is 180 degrees, when you make a straight line. Okay? You don't think of that as being an angle, but it is a 180 degree or a pi, an angle of pi. Okay? So here's, if this is alpha, guess what? They said they both have to be positive, so what else do they have to be? If the sum is 90, or pi halves, guess what is true about both of these angles? They're acute. They both must be acute. If they're positive, that means they both have to be less than 90 to add to being 90, okay? Or less than pi halves to add to being pi halves. So they both have to be acute. But to be supplementary, if one's acute, the other's got to be, what was the other term? Obtuse. And if one's obtuse, the other has to be acute. Neither one of those could be beyond 180 or pi radians. Okay? So one has to be acute and one has to be obtuse. Unless, there's one exception to that. What other two angles are supplementary that are neither acute or obtuse. If they're both right angles. Okay, they add a pi. Okay. If their sum is pi. Okay, does that make sense? Just a couple of nomenclature features here. Now, I believe, yes, they skip example 2. So let's go back and we'll do, goodness, I got to find a slide with a lot of white space on it. I don't see one. I'll use this slide. It's beyond where we are, but we'll do it. Let's do example 2. Now, I forgot to bring my watch in, so will somebody please let me know if I run over? Boy, y'all are kind to do that. Okay. Very nice. Okay. Example 2. What is the complement of 2/5 pi? So our angle, what you want to name that angle? You pick any name you want for it. What do you say the most famous one or the favorite one is? Okay, theta. Okay. Theta equal, okay, 2/5 pi. Okay. What is the complement of theta? What you know has to be true? The sum has to be. So if this is added to some other name, theta, we'll call it theta complement, the sum has to be what? Pi over 2. Now, what's wrong with that equation? Okay, I'm going to scrub that out for now. What's messy about it? The denominators, yeah. We love our fractions, but, it's just a little messy. What can you do to clear those denominators? Multiply by what? Okay, yeah. Multiply by the least common denominator, which will be 5 times 2 is 10. So if you multiply this by 10, and this by 10, and that by 10, that's legal in most states, right? Okay. So this will give you, that'll be 2, so this will be 4 pi plus 10 theta complement is equal to, and this will be 20 pi. Ooh. No, that's 5 pi. Okay, I thought that was a 4. 5 pi. Right? Do the subtraction. That's, if you can't read my writing, it's 4 pi plus 10 complement of theta is equal to 5 pi. And then what would we do? Solving for theta complement. Pretty easy. Yes, again? Subtract 4 pi from both sides? Is that what I heard you mumbling? Saying? Okay. And what does that give you? 10 theta c is equal to pi. Okay. And then what? Solving for theta c? Divide by 10. So theta c would be pi tenths. That's a positive angle, right? And it happens to be the complement of 2/5 pi. Well, let's see if that's true. Pi tenths plus 2 tenths in terms of 2/5 pi in terms of tenths would be 4/5 pi, right? So 4/5 pi plus 4 tenths pi plus 1 tenth pi would be 5 tenths pi, which is pi halves. Yes, that's right. Got it? What's the supplement of 2/5 pi? okay, let's call it theta s for the supplement of that, that's equal to pi. Okay? Now, there's other ways you can do this. This, to me, easier is just use the 5 and make this 5 pi fifths, right? And now I can just do a simple subtraction, and what do you get theta s to be? Someone I thought said it. It's easy. What must theta s be? If 2/5 pi plus theta s is 5/5 pi, 3/5 pi. Perfect. You just subtract 2/5 from 5/5. You get 3/5. So there's a supplementary angle to 2/5 is 3/5 because they add to be pi, which is 5/5 pi. Right? Yay or nay? Yay. Okay, good. You got it? Any questions? If you have questions, good time to ask. What's that? Okay. All right. Now, that was the A part. The B part is, let's do the same thing with theta equal 4/5 pi. I'm going to erase all this if that's okay. Everybody got it? Okay. So now we got theta equal 4/5 pi. Okay? What is the complement of 4/5 pi? We're looking for theta c. What must be true of that? Yes? Okay, so 4 pi over 5 or 4/5 pi, both of those. What? My hearing is so bad I can't.
Did you make that number up?
Make it what?
Did you just make it up?
Oh no, it's in the book. This is the B part of the problem in the book. Problem, example 2. I could have made it up, but I didn't. I wish I had. It's from the book. It's example 2B. Okay? So what is the complementary? That's supposed to be a C there. It looks more like an L. Okay. It's what? 2 pi? Is that what you said? No. Okay, no, you think you. Okay. What must be true of the complement of that angle? What's that? Yes, it comes, and we're dealing with theta pi's here, so we're not dealing with degrees, we're dealing with pi over 2. So then that 4/5 pi plus whatever theta c is must equal pi halves. Right? That's what we're saying. The angle plus its complement must be pi halves, right? As soon as you see a problem with this, let me know, but let's proceed. What would we do to solve that equation? Multiply everything by 10, is that what I heard? Okay, we did that before and it worked. So let's see if it works now. So 5 will go into 10 too. That would be 8 pi plus 10 theta c, complement of theta, is equal to 5 pi. Okay, now what do we do? Say again? Subtract the 8 pi, isn't it? Subtract 8 pi from both. We're trying to solve for theta c. So subtract 8 pi from both sides. Anyone see any problems coming up? 10 theta c is equal to, anybody? Negative 3 pi. Okay? Anyone see any problems? Complementary angles are always positive. Okay, what's wrong here? We did the steps right. How are we coming up with the wrong answer? If we carried it on out, we'd have theta c is equal to negative 3/10 pi. How do we mess that up? We can't have that. The complementary angle is always positive. A little louder. Yes, it is. That was an obtuse angle. Remember the other thing about complementary angles, it must be acute angles. You can't have an obtuse angle and have a complement part. It's already greater than 90, or pi halves. So therefore, yeah, it can't have a complement. Can it have a supplement? Yes, what would be a supplement? Theta C would be what? You can almost do this in your head, I hope. Oops, theta S, theta S. I already did. C couldn't exist, so theta S is what? 1/5 pi. You got it. It's pi over 5. 1/5 pi. Because then you add that to 4/5 pi, you get 5/5 pi, which is pi. And that is two supplementary angles add. And one has to be acute, one has to be obtuse. And the 4/5 is obtuse, 4/5 pi is obtuse, 5/5 is acute. Okay. Got it? There's another checkpoint. Please do the checkpoints as soon as you can after class so you fix it in your brain.
Question about that real quick.
What's that?
Did you just subtract that, you said? The complementary together?
Okay, it doesn't have a complementary angle because it can't be negative. The reason is because this is obtuse. Two complementary angles, both of them have to be acute. So this one started off being obtuse, so it can't have a complementary angle. There's no positive angle you can add to an angle greater than 90 and get it something to 90.
You just subtracted 4 pi to get that, right?
Yeah, oh yeah, okay. To get this one?
Yeah.
We did, if I had written it out, I did 4/5 pi plus theta S is equal to pi. So, and that would be 5/5 pi, subtract 4/5 pi, and you get pi. Exactly. I should have worked it out, but somebody answered, so I wrote it down. I'm lazy, okay. By the way, for those who haven't been in my class before, I have this theory about mathematicians. To be really good in math, I think it requires you to be just a little bit lazy. Do any of you qualify? No, you're all hard workers. You can still do it. Don't let that deter you. But if you're a little lazy, you're always going to try to find the easiest way to do the problem. So that's what makes a good mathematician. Okay, how are we doing time-wise? 11:12. Well, we got 3 minutes. No, wait. Yeah, wait. Yeah, we got 10 to 11:15, so 3 minutes. So let's talk about degree measure. We already know it pretty much. The second way to measure an angle is in degrees, denoted by this little symbol, a superscript circle. Okay? Now here's a bizarre thing. We use the same name, degrees, to talk about temperature and to talk about angles. We use the same symbol to represent degree. Okay? I don't know why. It seems like there'd be plenty of words and symbols out there, but we do that. So a measure of 1 degree, and the best I can figure, you have to blame the Sumerians. Who? The Sumerians. These were ancient people, predecessors of the Babylonians. Okay? They, for some reason, based things on 6, not 10. Well, they sort of use 10s and 6s. So 10 times, 6 times 6 is 36, times 10 is 360. I don't know what their basis was, but they did things in terms of powers of 6 with 1 power of 10, okay? They did it for degrees. They did it for, angle degrees. There's a bunch of things that have filtered down to us that are basically base 360, okay? So, one reason is everything is divisible in the 360. 1, 2, 3, 4, 5, 6. Not 7, but so many numbers are divisible in the 360. Maybe that's what it is. I don't know. But a measure is 1 degree is equivalent of a rotation of 1/360th of a complete revolution about the vertex. In other words, it takes 360 of those degrees to go all the way around. Yeah, that's what we know. To measure angles, it's convenient to mark the degrees on the circumference of the circle, like this. 0 degrees here, 360 degrees here. Half of 360 is 180. Half of 180 is, and half of 90 is 45. A third of 90 is 30. Okay. And those are our favorite ones again. Same ones we use for the radian measures, only now with degrees. 30, 40, 0, 30, 45, 60, 90, 121. Yeah. You just add your appropriate number to each of those. Now these aren't evenly spaced. The 45s are halfway between the 30s and 60s, but we don't do the 15s and the 75s. We don't do those otherwise. So this is a good way to go with it. Now you might think, why? Well, these are going to be so easy to deal with in our trig functions. We love them. Okay. Now, I guess we're going to have to start next time with conversions between, let's see if that's where we start. Well, a little bit earlier. Okay. We'll start right there, somewhere around there. Okay, that's where we'll start next time. All right, any questions? Let's see if there's a few homework exercises you can do. Let's see. Oh, I believe so. On page 267, odd numbers 7 or 9. And by the way, I'm going to give you odd number exercises. 2 reasons. First, the odd number exercises have their answers in the back of the book. Second reason is that the odd number exercises, if you look at the top of the exercise, see calcchat.com for tutorial help and worked out solutions to the odd number exercises. So try to do the odd number exercises. If you can't get the answer in the back of the book, then go to calcchat.com. Free website. You don't need any codes or anything. Just go to it. You have to navigate your way around it, but you can find that. You can do that pretty easily and see worked out solutions. If you still don't figure out why, then come bring it up in class. So I think you could do 7 or 9. Do 11. It has 2 parts. Do 13. It has 2 parts. Do 15. By the way, if you'll notice here, 15 has something special on it too. If you got your book, you'll see that 15 is in red ink. Well, what does that mean? That means there's another website you can go to. It's called CalcView, CalcView.com. And that will be there. Or, notice what this is, a QR code, right? If you got your cell phone, you can take a picture of that. You'll go straight to the website on your cell phone. Okay? So you can see even more detail about it there. So do 15. It's both a CalcChat and CalcView. Either 17 or 19, they're both a CalcChat, but 17 is a CalcView. We'll stop there. Oh no, I think you can do 21 and 23. They're both a CalcChat. You can do 25, I believe, it's a CalcChat. And I think you can do 27. It's a CalcChat. I think you can do 29. It's a CalcChat and CalcView. And 31 or 33, they're both a CalcChat. 33 is a CalcView. We'll stop there. We'll pick up the rest of it. Okay, good deal. Any questions? Yeah. That is on pages 267 and 268. Yeah.
Can you show me which one you got complimentary and supplementary one time where you get those numbers from?
Okay. All right. You probably saw the picture of it.
When I was looking in the book, it didn't make that much sense to me.
Right. Okay. Oh, well, I couldn't find that. I didn't put my finger. Okay. So, were you looking at this?
Yes.
Okay. The complementary angle to this one is add the complementary angle to this, and you get to pi halves. What they did was then take pi halves, subtract from it 2/5 pi. I was doing it the other way. They could do it this way. Well, to get common denominators, that would be 10. That would be 5/10 pi minus 4/10 pi. That would
both
be,
those numbers came from the books.
Yeah, the 2/5 pi came from the book.
And
the complementary angle of that.
Well.
The pi halves, that's from the definition of complementary angle. Add to be pi halves. So this one was, and then you did the supplement of 2/5 pi. then this one was 4/5 pie, and that came from the book. They just,
So the book
Yeah.
gives you.
it gives it to you, but shows you how to do it at the same time. I wish they'd have put the question there, what is this? And then you've seen it, and then they give the answer. They gave the answer as the problem, which to me is weird.
I gotta ask about science class. So, as far as I know, let's say 2 pi thirds, for example, and you say add 2 pi radians to that, or like
Okay.
all the way around.
Okay, 2/3 pi. Is that where you're starting?
Mhm.
Okay, 2/3 pi. And you add 2 pi to that, one way around, right? Is that what you're wanting to do? Well, get this in terms of thirds. That would be 6/3 pi. That's 2 pi, right? And add those two together, you get 8/3 pi. Add the numerator, keep the denominator. Yeah. Is that what you mean?
Yes, sir.
Yeah, got it.
I have a question not about math.
Yeah.
I know you have a lot going
No,
on.
about the,
Yeah.
yeah.
I just, I went around and asked if like there was a certain form. And
Right.
They said that there's not.
There's
So
not.
I guess I just need like a personal recommendation.
Right.
So just whenever you can do it,
Okay.
if you want to.
But who do I write it to, or, I mean, what am I doing?
I guess it's to Honda, like it's to Honda.
To Honda, okay.
Yeah, it's for internship on engineering. For
Okay,
Honda.
okay.
Just whenever you get a chance.
Okay, but you don't have anyone's name I write it to, it's just to, just
I
Honda.
can get his name. It's like it's Keith something.
Okay, yes, sir.
Oh, I have a research paper.
Oh, look at that, my goodness. All right, I love to see it.
So,
Okay.
did you ask for a full page printed out of like just the source we use?
Yeah, one page from one of your sources, you got
That's
it.
what it works out.
Okay, I think you did more than one page, yeah. Very good, excellent, thank you. Jumping right on it. Okay, excellent.
That's what we got to do.
What's that? Research paper, yeah.
When to do?
By the end of the term, but do it sooner than that, as soon as you can.
Bonus points you turn in early, right?
Yeah, what's that?
Don't you still get
Yeah, you get bonus point, 4 bonus points for turning in January, 3 for February.
We find that on class handouts or something. We find it.
Yeah, handouts. Well, it's 2 handouts, PowerPoints, and more. That tab, and you'll see both. You'll see the YouTube videos there. If you go and listen to the one where I tell you about it, you can hear me talk about that. Or right below that, you'll see research paper instructions. You can read them there if you want to. You can hear me talk about them and read them on the YouTube video, or you can just see them over there.
Yes, sir. All right, I got a name.
Okay. But if it's helpful, I don't know if it is or not.
Yeah, it probably will be.
Okay.
So the guy's name that I guess I'm doing the internship with is Scott Hayward.
SCOTT, what?
Hayward, H-A-W.
Oh, Haywood.
Yeah.
Haywood. He wouldn't happen to be South African background, would he?
I have no clue.
Yeah, okay. Because we do some Haywoods in Birmingham who he was a pastor, but he is, maybe even his wife has died. But I know he has died, but they could have had kids. I just wondered if it was the son of that. Scott Haywood.
Yeah, I don't know. I'll just talk to him on the phone right now.
Right,
I'm really hoping I can get this internship because it'd be really good for me.
right.
To have experience at
Always good.
Honda for engineering,
Right.
would be really good.
Yes, excellent.
Then they pay $15 an hour, so that's good.
Oh, that would be all right too, huh?
Get a little extra.
Maybe
Get
maybe
out the
not
rest.
not any more than
Yeah, not any more than what I'm making over there. But
oh, I'm sure it's not.
I'm ready to get out of the restaurant business. Trust
Right,
me.
okay.
This is really
Into engineering, yes.
Yeah.
All right.
I'll see.
Okay, I'll try to get this done maybe tomorrow morning. It may be Friday morning. Okay. Because I don't have many other office hours except those two.
I know you got a lot to do.
Okay, yeah.
Thank you so much.
Sure, glad to. And we recorded all that.